Hi and welcome back. So in this video, we're going to go through some algebraic examples with matrix transformations. I'm going to start with one example, then do a little bit of new information, and then end with an example that uses that new information. So for our first example, we're just going to consider a matrix transformation T of x equals A of x, where the matrix A is the following. So the first row is 5, negative 2, 3, the second row is 7, 0, 1, and the third row is negative 1, 4, 6. So we're just going to explore this matrix transformation a little bit and input some specific vectors and see what their outputs are. But before we get to that, let's talk about the domain and the codomain. So I like to explore the dimensions first and make sure I really understand all the dimensions that are going on. So if we're going to input a vector into this function, it's going to need to have the right dimensions to be multiplied by this matrix A. So A is a 3 by 3 matrix, and we need a vector that inputs. So it's going to need to have 3 components in it in order to have those inner dimensions match on the multiplication. So we're doing A to be 3 by 3, and X to be 3 by 1. Then when we do this multiplication, we're getting a 3 by 1 vector output for our B. So this tells me that the domain is R3, since our input vector X has 3 elements. And then our range, or our codomain, is also R3, since the resulting vector will be 3-dimensional too. Normally in this setting, someone will tell you what the domain and the codomain are. That's standard practice to let you know where we're starting and where we're going. But in case that doesn't happen, it's nice to be able to make sense of the dimensions and figure out what an appropriate input and output would be. So let's try to find t of 1, 0, 0, then t of 0, 1, 0, and lastly t of 3, 2, 1. So these first 2 vectors are special vectors that we're going to talk about after this example. Then this last vector is just something I picked, 3, 2, 1. So for our first input vector, we're putting 1, 0, 0 into our function. What our function t does is it takes the matrix A and multiplies it by the vector. And so we're looking at our matrix A and then multiplying by that vector 1, 0, 0. Now, if we're jumping straight to the algorithmic way to do this multiplication, I'm going to do 5 times 1 minus 2 times 0 plus 3 times 0, then 7 times 1 plus 0 times 0 plus 1 times 0. So I'm just going row by row. Then negative 1 times 1 plus 4 times 0 plus 6 times 0. So since we only had that 1 in the first position, those are the only terms that are coming out. So we're really taking 1 of the first column and 0 of the next 2 columns. So we're getting 5, 7, negative 1 as our resulting vector. So what this input vector 1, 0, 0 did was give us just the first column of A. So 5, 7, 1 is that first column from A. Now let's look at our second input vector. So let's look at 0, 1, 0. You might take a moment to hypothesize what you think this vector might give us as a solution before you go through the algorithm. So what T does is it takes the matrix A times that input vector, and so we're going to write the matrix A here times our 0, 1, 0. Then if I do the algorithmic way of doing the multiplication, I'm doing the first row times our vector, so 5 times 0 minus 2 times 1 plus 3 times 0. Then I do the next row, so 7 times 0 plus 0 times 1 plus 1 times 0, and the third row, negative 1 times 0 plus 4 times 1 plus 6 times 0. So here, since I have a 1 in the second position of the vector, I'm just taking 1 times the second column. So I have 0 of the first column, 1 of the second column, and 0 of the third column. So my final solution is just negative 2, 0, 4, which is exactly the second column of my matrix A. So this vector gave us an output, which is negative 2, 0, 4, which was the second column of our matrix A. Now let's try one that's a little different. Let's do T of 3, 2, 1. So again, our transformation T takes the matrix A and multiplies it by the input. So we're going to write our matrix A here and do the multiplication times the vector 3, 2, 1. So doing this, I'm doing 5 times 3 minus 2 times 2 plus 3 times 1. So that's my first row times the vector. Then I do 7 times 3 plus 0 times 2 plus 1 times 1. That's the second row. And then lastly, I do negative 1 times 3 plus 4 times 2 plus 6 times 1. That's the third row. So you can see here that we're doing 3 of the first column, 2 of the second column, and 1 of the third column. Now, when I put these numbers all together, I'm getting 15 minus 4 plus 3, which is 14. Then I'm getting 21 plus 0 plus 1, so 22. And then negative 3 plus 8 plus 6, which is 11. So 14, 22, 11 is my final answer for the vector. So what inputting 3, 2, 1 did was that it took 3 of the first column of A, added it to 2 of the second column of A, and then added it to 1 of the third column of A. So I think this is just a nice way to unpack this information so that you're not just seeing the input and the output, but really thinking about what the input does in relationship to the matrix A. All right, so I want to talk a little bit about those special vectors where we just had one value that was 1 and the rest of the values were 0. So in general terms, we call the vectors where we have 1, zeros in the rest of the spots, 0, 1, zeros in the rest of the spots, etc., all the way where we have zeros in the first positions and then 1 in the very last one. These vectors, with however many dimensions they have, we call them basis vectors, and we label them E1, E2, all the way through En. So E1 would have a 1 in the first position, E2 would have a 1 in the second position, and then En would have a 1 in the nth position, where the rest of the values were all 0. So we would say that EI has all zeros with a 1 in the ith component. So if you've worked with vectors before in maybe a physics or a calculus setting, you've probably seen this in 3 dimensions with I hat, j hat, and k hat. So I hat would be the vector 1, 0, 0, j hat would be the vector 0, 1, 0, and k hat would be the vector 0, 0, 1. So these are our basis vectors in R3, where I hat is E1, j hat is E2, and k hat is E3. They just use different names in different settings. So we can have these vectors E1 through En as our basis vectors in whatever dimensional space we're in. So what's cool about these vectors is that a matrix transformation is actually defined by what it does to these basis vectors. So let me explain what that means. If we take the first basis vector, E1, and we input it into our transformation, what we're doing is we're doing A times that vector. And so if we think about the columns of A being V1 through Vn, and then we're multiplying by that vector with a 1 in the first position and zeros in the rest of the positions, we then are doing 1 times V1 plus 0 times V2, and then we're doing zeros of all the columns all the way until we do 0 times Vn. So we're really only looking at that first vector. So the only thing that comes out of this matrix transformation is just V1, which is the first column of A. So by inputting the first basis vector, we are being output and told the first column of our matrix A. And that matrix A is what defines our transformation, right? That is the thing that determines what happens to our inputs, is that matrix. And so by inputting the first basis vector, we're sort of being able to isolate that first column of A and determine what it is. We could then do the same thing for the second column of A by using the second basis vector. So we could input E2, and so we would be doing the matrix A times that vector with a 1 in the second position. This would mean we would get 0 times V1 plus 1 times V2, and then we would add 0 of all the rest of the columns all the way until 0 times Vn. This would output just V2, which is our second column of A. So by looking at what T does to this special input vector, we're outputting just the second column of A. We could repeat this for any of the basis vectors. So in general, T of EI, where that's the ith basis vector, will give us the ith column of A. So we could actually write A in terms of what happens to the basis vectors. So the first column of A is T of E1, the second column of A is T of E2, all the way to the final column, which would be T of En. So this becomes useful if maybe we only have a limited amount of information about what the transformation does. Or just depending on what information we're starting with, it's nice to be able to input something into the transformation and get an output that tells us what we want, which might be one of the columns of A that we're trying to find. Let me show you an example of this. So let's suppose that we have a transformation T that goes from R3 to R2, such that we know that T of E1 is the vector 3, 5, T of E2 is the vector -9, 0, and T of E3 is the vector 1, 1. So we know what the transformation does to all the basis vectors, and now we're going to find the matrix A that describes the transformation. So that would be where T of the vector x is equal to A times the vector x. So as I like to do, I like to make sense of the dimensions first. So we're starting at R3 and going to R2. So that means T is taking an input vector with 3 components because it's in R3. So it's taking something like x1, x2, x3 and multiplying it by A. So let's just make sure we know what the dimensions of A should be. So our input vector is 3 by 1. We're getting an output that is 2-dimensional, so it's something like B1, B2. And so we're going to need a 2 by 3 matrix in order to make the dimensions work. So the answer we're looking for A should have 2 rows and 3 columns. Then what we just talked about before this is that the columns of A can be found by looking at what T does to the basis vectors. So T of the first basis vector, E1, should be our first column, T of the second basis vector is the second column, and T of the third basis vector is the third column. So it's as simple as just taking the vectors we were given and making them into the columns. So the first column is 3, 5, the second column is -9, 0, and the third column is 1, 1. And there we go. So that's our matrix A that represents this transformation. Alright, so that's an overview of what we can do algebraically with matrix transformations. Thanks so much for watching, and I will talk to you in the next one.